Welcome to Chem Help ASAP. This video provides practice problems on distinguishing one structural isomer from another based on a proton NMR spectrum. We will emphasize four features of the spectrum: the number of signals, chemical shift, multiplicity, and integration. The video description contains links to printable copies of these problems and their solutions. Furthermore, links during the video will connect you to other potentially helpful videos. Before we jump into the problems, let's review the key features of an NMR spectrum that we will use to distinguish one isomer from another. First, the number of different signals is very useful. At most, each hydrogen can generate one signal, but symmetry within the molecule means that the number of signals is smaller, as some signals will likely overlap. The second trait is the chemical shift. The chemical shift refers to the position of a signal along the x-axis and is determined by the electronic environment around the hydrogen. Terms like upfield, downfield, shielded, and deshielded are common when discussing a signal's chemical shift. The third trait is multiplicity, which is the pattern of the signal. Singlet, doublet, triplet, etc., and is determined by the number of neighboring vicinal hydrogens on adjacent carbons. Finally, we have integration. The more hydrogens that contribute to a signal, the larger that signal is based on the area under the peak. The area under the peak determines the integration. Of all these features, I would strongly recommend spending some time to memorize the representative chemical shift values. Aromatic CHs, aldehydes, alcohols, etc. Memorizing these values takes some time, but knowing typical chemical shifts is extremely helpful for analyzing NMR spectra. The different spectra in this video were generated by the website nmrdb.org, a fantastic resource. Alright, as we work through these problems, I am not going to follow a specific set of steps. I tend to do these problems by feel. If you are looking for the best steps for interpreting spectra, then I don't have that. Hopefully, if you watch all these problems and solutions, you will see multiple different approaches to answering these questions. You can then rely more on a specific method if that one works better for you. Okay, let's go. Here's the first problem. Now, when I see a spectrum, I first look at the spectrum. I'm not going to look at the structures below the spectrum. Let's just get a feel for what the spectrum is showing us. So what stands out to me is I see three signals. Now it's possible that this really isn't three signals, that some of the signals are different yet overlapping in a strange way, but to me these signals look fairly clean. That's a nice clean doublet. That looks like a nice clean doublet. This is probably three signals, so three different types of hydrogens in the molecule. So it's a fairly simple molecule. Then I'll look at the integration. This looks like two hydrogens, 1 and 6. And 6, that's a pretty big number. So there are a lot of identical hydrogens. 6 is 2 times 3. Anytime you see 3s show up, that often means methyl groups. So this 6 looks like two different methyl groups, or two methyl groups that happen to show up in the same place. Okay, so now let's look at the molecules we have and see if this can clarify anything. Our first structure on the left, this molecule should have this CH2, maybe that's signal A, B, C, D. So on first glance, this molecule, this leftmost molecule, looks like it should have 4 signals. It's not guaranteed, but that's what it looks like at first glance. I don't think this spectrum matches this first molecule because our spectrum has 3 signals. So let's tentatively eliminate this structure. Okay, our next structure. Let's see, there's a CH2. That should have a signal. This CH between the methyl groups should have a signal. And then we have a methyl and another methyl. These two methyl groups are identical by symmetry. Okay, so this molecule should have, we would expect, 3 signals. So that's a possibility. Now let's keep working to the right. We have this molecule. This molecule has 3 methyl groups And all three of these methyl groups by symmetry are identical. So this molecule should have just one signal. Now it's going to be one big signal because all three of those methyl groups, that's a total of 9 hydrogens, and that's going to be a big singlet because they don't have any neighbors. But it's one signal. That doesn't match the spectrum that we have. So it's looking pretty good for molecule B. Now let's look at this last one. So that methyl, B, C, and D. Now notice we have two methyl groups, A and D. And I've said they're different. I've said they're different because I gave them different letters. And you might say, hey, methyl groups, they're all the same. Well, no, they're not all the same. You know, this methyl group is attached to a carbon, just a CH2. This methyl group is attached to a CH with a chlorine. That's going to change its electronic environment and probably, not certainly, but probably means A and D will not be in the same place. Now, is it impossible? No, but A and D will likely be different. But let's just leave a question mark here and leave that option open. And now we'll let the spectrum give us more information to help us distinguish. Do we have the second compound or the fourth compound? Okay, so let's look more at our spectrum. We have, let's focus back on this big signal, 6 hydrogens. So we have these 6 hydrogens together. This could be a CH3, which is a singlet, not signalet, but a singlet, and another 3 hydrogen singlet that happen to be right next to each other. So, you know, this could be 2 separate methyl groups. Oh, that kind of sounds like this, 2 separate methyl groups. But they would need to be both singlets, meaning they have no neighbors. Well, that doesn't fit this compound because methyl group A has a neighbor. So methyl group A would be a doublet. Furthermore, methyl group D would be next to the 2 hydrogens on C. So that would actually be a triplet. These singlets don't match, okay? Instead, what this 6 hydrogen doublet looks like is it looks like a doublet, and I just said it. This looks like our 2 CH3s with 1 neighbor, and so that's a doublet. That's a doublet by symmetry. They land on top of each other. That's 6 hydrogens all together. There's a doublet. So I think we can eliminate this last compound, and we're definitely here. Let's finish the spectrum and just see what we have. So I mentioned we have this hydrogen has a ton of neighbors. It has 3 here, and 2 on position A. So that's a total of 8 neighbors. It's going to have all kinds of multiplicities. It's going to be split like crazy, and that's pretty much split like crazy, and it's also 1 hydrogen. That's a good match. Now notice these 2 hydrogens. That's a CH2. There's 2 hydrogens. We're saying it's a doublet, or the spectrum says it's a doublet. It does have 1 neighbor, so those should be a doublet. And furthermore, they're further downfield because this chlorine is next door. And chlorines and oxygens, typically based on their electronegativity, they're doing an inductive effect. That causes de-shielding of the carbon and those CHs, and that moves these down to typically between 3 and 4. That's the typical range. So everything looks good. This is almost certainly our second compound. That's our answer, which on the question handout would be B. All right, problem 2. Let's see if we can work through problem 2 a little faster than we did problem number 1. So again, let's look at the spectrum. So we see what seem to be 4 different signals. These 4 hydrogens, and I'm looking at the integrations, those red numbers, 4 hydrogens, 2, 3, and 3, and I always think when I see 3s, very often those are methyl groups. So we're going to have a molecule that probably has 2 methyl groups, and since they have a different chemical shift, they're going to be distinct methyl groups. Now, let's look down here at this 4 hydrogen signal. And this may not be one signal, maybe it's something overlapping, but notice it's at about 7 ppm between this 6 and 8 window. That's an aromatic ring. And of course, if we look below the spectrum, we see lots of aromatic rings. Now, the integration can be extremely helpful. So what this tells us is we have an aromatic ring, because that's where the chemical shift is, and we have 4 hydrogens. You only get 4 hydrogens on an aromatic ring if you have a benzene ring that has 2 groups on the benzene ring, which means there are only 4 spots left over for hydrogen. So let's immediately look at our structures at the bottom. This first structure has a benzene ring, and that benzene ring only has 1 substituent on it, meaning it's going to have 5 hydrogens on the ring. 5 hydrogens would not be 4 hydrogens. So we can eliminate this compound immediately just based on the integration of the aromatic region. Let's look at our next structure. Here's a benzene ring that is monosubstituted. This benzene ring will have 5 hydrogens on it. We can knock that out of consideration. This is getting great. Okay. Now, this next structure, this is a tri-substituted benzene ring, meaning it has 3 substituents, meaning it has 3 hydrogen substituents to fill out the rest of the ring. This would have an integration of 3. That is not 4. It can't be that one. Now, let's look at our last structure. We have a benzene ring, and it is di-substituted, meaning we have 1, 2, 3, 4. We must be this last answer. So that's answer D. Now let's look at what else we see. So I said, oh, here are these 2 peaks that have integrations of 3. That's very often, not always, but we'd expect to see 2 methyl groups. And that's exactly what we have. We have a methyl group here. Note that this methyl has no neighbors. There are no hydrogens on that neighboring carbon. So this should be a singlet. And that's exactly what we see. This is a 3 hydrogen singlet. Okay, that makes sense. And here is a CH3 group. There's our integration of 3, and that signal has 2 neighbors. This is the n+1 rule. 2 plus 1 is 3, so this CH3 group ought to be a triplet, and that is a triplet, so that looks good. And finally, let's address these 2 hydrogens right here. Notice we have 2 left. That's exactly what our peak is. It's 2 hydrogens. These 2 hydrogens have 3 neighbors based on that methyl group. 3 plus 1 is 4, so these 2 hydrogens should be a quartet, and indeed they are. Okay, so our correct answer for this problem is D. Okay, before we do problem 3, I need to make an admission. I have doctored this spectrum. So NMR-DB, and I love the website. However, NMR.DB does not make a prediction for OH and NH groups. And you can identify those typically in an actual spectrum, not a simulated spectrum, as being broad peaks. This broad peak right here is from an NH or OH. And if you look to the bottom of the screen, you can see it's going to be an NH. So this signals from an NH. NMR-DB does not generate this. So instead, I went into Paint, and I stuck that peak in there, and it has an integration of 2. But if you were to take the final answer from this question, put it into nmrdb.org, and generate a spectrum, you would not see this signal because nmrdb.org does not do OHs and NHs. It only shows CHs. So that's our one disclaimer. Now let's look at this spectrum. And I've already highlighted what I think is the most interesting signal here. We see a bunch of signals that have really nice, clear multiplicity, which is what you typically see on CH peaks. And then we kind of see this blob, which is what you tend to see for OHs and NHs. Now, that depends on what solvent you use, but for most spectra in introductory organic chemistry, you use solvents that give NHs and OHs sort of as broad peaks. So we have a broad peak that's an NH or an OH, and it has an integration of 2. Okay, that's very helpful information looking at our structures at the bottom of the screen. Because if we look at our first structure, that only has 1 NH. That wouldn't give an integration of 2. So we can't be this signal. But only based on this one peak, we can already eliminate that structure. And this is why I tend to look at the spectrum and I look for information that's going to be as helpful as possible. Let's take as many compounds or possibilities off the table as quickly as we can. And as it turns out, based on the structures we're given, that's really helpful information. Now, again, this is an NH with 2 hydrogens. We look at our next structure. Oh, this has an NH2. That is a possibility. We haven't looked at the rest of the spectrum, but that at least belongs under consideration. Our next structure also has an NH2, so that's a possibility. Our last structure doesn't have any NHs, so we can eliminate that from the get-go. So now we're down to 2 possibilities, and we need to look at the other peaks. So let's, I tend to gravitate towards these methyl groups if I can. So here we see there are 2 different methyl groups in this structure. So if we look at this second structure, which is answer B on the sheet, we can see that, well, okay, these NHs should show up. There's a CH2, there's a CH. That methyl and that other methyl are the same by symmetry. They're going to overlap. So we shouldn't see 2 methyl groups for this second structure. We should just see 1 6-hydrogen signal for both those methyl groups. That is not what we see. We see distinctly 2 methyl groups. So let's, before we eliminate that structure, let's go to the other one and make sure that the other one is going to give us this multiple methyl groups. So let's go over here. Let's just label these A, B, C, D. The NH2 is E. So this would, if we're correct, this is almost certainly going to be signal E. That's our NH2. Now, we do have 2 methyl groups. These don't look identical, or we wouldn't predict they'd be identical by symmetry. So seeing 2 different ones is completely reasonable. The signal for A has 1 neighbor. That's that hydrogen on B. Therefore, A should be a 3-hydrogen doublet. And we have that right there. So that's reassuring. Now let's make sure the other methyl group also lines up. So for D, we're going to have 2 hydrogens on C. 2 plus 1 is 3, so we'd expect signal D to be a triplet. And it is. So that's reassuring. Okay, our methyl groups make sense, and I think we can safely eliminate the second structure. Now let's go ahead and assign the rest of the spectrum. Peak A, we've already assigned that, so let's try peak B. Peak B, that's a hydrogen that has neighbors on A and C. That's 6 neighbors. I'm sorry, it's 5 neighbors. 2 on C, 3 on A. 5 plus 1 is 6. So we see this high multiplicity signal, and it is 1 hydrogen. That looks good. And then let's look at these 2 CHs. So they have 4 neighbors, and we see a multiplicity of 5 for that peak. And again, the integration works. Now, one last comment on NHs and OHs. When I was counting hydrogen neighbors for B, I only counted the carbons. I did not count the nitrogen. It depends on how you run your NMR spectrum. It depends on the solvent. NMR-DB assumes you're using a solvent where you won't see multiplicity that is contributed to by the NHs and OHs. Depending on the solvent, you might see it. So I'm saying this has, signal B has 3 plus 2 neighbors, 5 neighbors total. It's possible you could get up to 7. Depends on the solvent. Okay, here's problem number 4. Just looking over the spectrum, what stands out? Not a whole lot. I will say this signal is pretty far downfield, but I like to focus on the 3s if I can. So there's a 3 and there's a 3. Looks like we have 2 different methyl groups in this compound. And, that's not a whole lot to work with, but let's go ahead and see what we have. So we look at the first structure. Let's see, A. Now B doesn't have anything. There's B and C. So again, this carbon doesn't have any hydrogen, so it won't show anything. But we do have a methyl and a methyl. Hey, at least by our criteria, this could possibly match. It's not unreasonable. Let's go to our next compound. Next compound, we have a methyl, and by symmetry, this other methyl would overlap. So these two methyl groups would have the same chemical shift and they'd overlap. They'd both be singlets. That is not what we see. Furthermore, aldehyde hydrogens show up at about 10 ppm, and this spectrum only goes to 5, which implies there's nothing at 10. So we can eliminate this structure. Now let's look at the next structure. We would have a signal for that CH2, and that CH3. We only have one methyl group in this third structure. So that's not a possibility. Now let's go to our last structure. A, there's a methyl. B, that's a CH2. C, that's a CH2. That doesn't have two methyl groups. So that is not a possibility. That doesn't match the spectrum. Now let's go back to our original structure. We think we know the answer. The answer is going to be A. But let's go ahead and assign it. So signal A, that's a CH3. There are no neighbors, so that should be a singlet. And we do have a 3-hydrogen singlet. Let's go to the other methyl group. Here's this CH3. It has one neighboring hydrogen right there. That should be a doublet. It is a 3-hydrogen doublet. Fantastic. That's signal C. And now let's look at this last signal, B. This has, let's put in the CH3. That hydrogen has 3 neighbors, so it should have a multiplicity of 4. Integration of 1, multiplicity of 4. That is B. Okay, so everything lines up. The answer for problem number 4 is A. Okay, problem number 5. Again, let's just take a look at our spectrum and see if there are any obvious clues that we can use to eliminate some of the possibilities. I see a 3. This is a very downfield 3, but that looks like a methyl group. And here we have a 6. It's 2 times 3. That's very likely going to be 2 methyl groups. And then we have this singleton hydrogen here around 2.5. Okay, so let's see if we can find a structure here that has 3 methyl groups. So our first structure has, let's label the number of different signals we'll have. That's a CH3, a CH2, a CH2, and a CH3. We only have 2 CH3s, so it looks like we are not. This has 2 methyls. This doesn't look that encouraging. Okay, let's look at the next structure. We should have A, B, C, D. And there's a methyl, and there's a methyl. Otherwise, we just have CH2s. This looks like 2 methyls. This is probably not our structure. Let's look at our third one. There's A, that CH is B, C, and, oh, I was going to label that D, but notice by symmetry, these two should be identical. So that's not a D, that's a C. Okay, that has 3 methyls. That could be what our spectrum is. Now let's look at our next one. We have A, there's B. Oh, okay, this methyl group is by symmetry the same as that one, so we'll label this A as well, and then that makes that C. So we have 3 methyls here too. These are both possibilities. So let's go back to our first one. We have these 2 methyl groups, and they have 1 neighbor, so that should be 6 hydrogens together as a doublet. And we have a 6 hydrogen doublet. Okay, and furthermore, we have this CH3 by itself. There are no neighbors from this oxygen, so that should be a singlet. Okay, that's a match. Let's see if the other compound can match that description. Here are 2 methyl groups. They both have 1 neighbor, so that should be 6 hydrogens as a doublet, and that's what we see. Okay, and then we have this CH3, and it has no neighbors, so that should be a singlet. Okay, these are not obviously different, but what is different about these is the position of, the one that stands out to me is this one. Look at this. This is way downfield. How did this CH3 get all the way down past 3.5 ppm? Well, it must be next to, directly attached to, a very electronegative atom. And if we compare our 2 structures, this one has the CH3 that is the singlet next to an oxygen. This CH3 is not directly attached to an oxygen. Now I know you look at this CH3 in the last compound and say, well, it's not next to an oxygen, directly next to, but look at these oxygens over here. They really don't have a big impact. It's what is the atom that's directly next door. For this CH3, it's just a carbon. For this CH3, it's an oxygen. The chemical shift of this signal is a much better match for our third structure, answer C. So let's look at this a little more closely. So how about for problem C, where would this peak show up? Now I just said this hydrogen, it's on a carbon and it's next to another carbon. Not very fancy, not very de-shielding, and notice that signal shows up around 2.5 or so. If our spectrum matched our rightmost structure, then this CH is right next to an oxygen. It ought to be way downfield, like past 3 and maybe into 4. But notice that peak is a little bit more upfield. So the position of this peak also supports structure C, not structure D. So we're going to eliminate D and go with structure C. But just by looking at the methyl groups, we could get the discussion down to C or D. So just looking at some key features can help narrow the structures that you're going to have to consider. Okay, here's our last problem. I'm going to play the same trick that I did on our previous structure that had aromatic rings. So if you notice, this spectrum has signals down, past 6.5, between 6.5 and 8. This is typically the aromatic region of a spectrum. And notice that we have a total integration of 5. We have multiple signals down here, but in aggregate, in total, we have 5 hydrogens. That means our structure needs to have a benzene ring that only has one non-hydrogen group coming off of it. So let's use that as our first pass to filter some structures. So as we look at structure A, we have 5 hydrogens on our ring. That's a possibility. As we look at structure B, we have 5 hydrogens on the ring. Okay, that's still a possibility. Structure C, it has 2 substituents on the ring. That means it has 4 hydrogens. We can eliminate this because we need a molecule that has 5 total benzene ring hydrogens. And as we go to our last structure, we again have a monosubstituted benzene ring. This is a valid candidate. So we've only eliminated one structure. Now I love looking at methyl groups. So here we are. This structure looks like it has 2 3s in it, two methyl singlets. So let's see which of the remaining compounds actually have 2 methyl groups in there, 2 methyl singlets. So now we look at our first structure. We have a methyl and a methyl. This is a possibility still. We look at our next structure. We have a methyl and we don't have any other methyl groups. This is less likely. And notice, this has an NH. Those NHs tend to be broad. We don't have that in this spectrum. This is not looking promising. Okay, now let's look at this last structure. This last structure should have a methyl, and there's no other methyl. Furthermore, it should have an NH, which we don't see in this spectrum. Therefore, we can likely eliminate this. Now let's just make sure everything makes sense based on what we've said. So here's our benzene ring. Those are our 5 aromatic hydrogens in the roughly 7 to 8 region. That looks good. We have 2 methyl groups. Let's label these as A and B. Now notice A is next to a nitrogen. That's a more electronegative atom. That's going to move it further downfield. And so this methyl singlet that's further downfield is likely A because it's attached to the more electronegative nitrogen that is de-shielding and causes the peak to show up at a higher chemical shift. B, however, is a methyl group and it's only attached to a carbon. It is less de-shielded and shows up at a lower chemical shift, and that is this signal right here. So everything makes sense as we look at the rest of the data, and everything is consistent with this first structure. So this would be answer A. I hope you enjoyed these problems and that they help you better understand how you can use NMR spectroscopy. Please subscribe to the channel, like this video, or leave a comment. Thank you for watching. Remember that links to these problem sets are in the video description. Take care.